Denver, Colorado is at a higher altitude than Los Angeles, California. Which of these statements is correct? Water boils at a lower temperature in Denver than Los Angeles. Water boils at a higher temperature in Denver than Los Angeles. Or water boils at the same temperature in Denver than in Los Angeles.
All right. Yeah, it's a great question. Super relevant since we live in Denver. Answering a question like this, right, is fairly straightforward. If we just want to know the answer, does it boil? I mean, if you just wanted to cook something, you could easily find something on the internet that would tell you. If we could jump to my screen, I'll just show you a really simple graph. So you might find a graph like this if you ask Google about boiling point compared to altitude. And you can see in this graph that we've got the temperature of the water in degrees Fahrenheit on the left, and then we have the altitude on the y-axis, I should say, and we have the altitude on the x-axis. And so you can see as altitude increases, and this has got us going from 0 feet altitude to 10,000 feet, the boiling point of our water decreases. So we typically hear that water has a boiling point of 100 degrees Celsius, which is 212 degrees roughly Fahrenheit. But you can see that here in Denver, Colorado, where we're at about 50 to 80 feet above sea level, I'm going to find that area just above 5,000 feet right here and come up to this line here on the graph, and it looks like you can boil water here in Denver at around 202, 203 degrees, so almost 10 degrees cooler than in Los Angeles. So again, it's fairly easy to just answer that question using the internet or just get that direct answer, but more important would be to understand why this is the case. So boiling has to do with what's called vapor pressure. So we think about the conversion between a liquid and a gas. We call that a phase change, and we can think of any kind of liquid has what's referred to as vapor pressure, and that's the pressure that the liquid exerts on the air around it to essentially allow its molecules to make a phase change from the liquid state to the gas state. Let me show a picture kind of that idea. This is really small. Let me blow it up here. So hopefully you can see. It might be a little bit unclear on your video screen. But you can see what's pictured here is a jar full of water, and you can see the water molecules down here are just one solid mass, but then we have water molecules floating up above here. And the idea goes that, that there's a natural pressure that this phase change is exerting from liquid to gas, that these water molecules are exerting on the air around it. If the air around it has really high pressure, you can see up here we have air pressure pushing back on the water. If the air pressure around the water that we're talking about is really high, that's going to prevent water molecules from moving from the liquid state to the gas state, from making that phase change. There's another image I can show here which might show this fairly simply. So in a liquid state, we can imagine molecules much more closely bunched together, and then in a gas state, they're spreading out from each other. And the energy that these molecules have, even in a liquid state, molecules are vibrating and shaking, and they have energy inside of them, and we perceive that energy as temperature. And even cool water that we might perceive as cold, even that is exerting some vapor pressure, and some of the molecules there are making that change from liquid state to gas state. And I should actually throw in too that there are some molecules, and you can see here that some molecules are going from gas state to liquid state. So there's this natural exchange back and forth. If the water's cooler, more of it is going to be inclined to stay in liquid state, and if it's warmer, more of it's going to be inclined to change over to gas state. But then what we really want to think about is, so how does this relate to altitude? So I'll just show one more graphic to kind of get this idea across. But the idea goes that when we're at sea level, which is as low as you can be on land, right, without being underwater, you have the most air above you. The atmosphere extends out from the surface of the Earth, and the lower elevation or lower altitude that you are, the more air you have above you, and the more tightly packed that air is. As you go further up in altitude, the air molecules get spread out more. This is why it's hard to breathe in really high places. People who are used to sea level levels of oxygen, when they get up to places like Denver or even higher elevations, they can have a hard time breathing. People who summit Mount Everest, which is over 20,000 feet tall, some of them actually need to bring oxygen tanks with them because the air molecules, the oxygen molecules in particular, are so scarce at such an altitude that folks are unable to breathe. Looking at this diagram, though, we can see that, again, down at sea level, there's a lot more air pressure, and that's because there's more air molecules weighing down. In fact, if you're down at sea level, you've got more air literally weighing on your body, although given that air is so light, we don't notice really any perceivable difference. But imagine a glass of water, or let's say a pot of water on the stove. If I'm down in Los Angeles and I've got a pot filled with water, as I turn on the heat, what I'm trying to do is increase the energy of the water molecules inside that pot. And when I increase that energy, the vapor pressure of the water will rise and will work to overcome the air pressure that's pushing back against, and I'll show that image again, that's pushing back against the water. Down at sea level, there's more air pushing down on the water, and so the air pressure is higher. So you have to bring the water to a higher temperature to increase the vapor pressure more, so that it can overcome that atmospheric pressure, and we can get to a boiling state where liquid particles are easily making the phase change to gas. Up here in Denver, we have less air overall, we have lower air pressure, and so that pot of water on our stoves at home has less air pressure pushing down on the surface of the water, so it takes less overall energy that we have to put in to get those molecules to get to a point where they've got a vapor pressure that can exceed atmospheric pressure. So again, just kind of thinking about the reason behind these answers. You know, a lot of the times the science questions that I get are questions that can be answered really quickly, like in a single sentence or maybe even just a single word. But the goal should always be understanding the science behind them, what's really going on at a molecular level or at a cellular level, as opposed to just trying to get the right answer.
I really liked that explanation. It made me understand it.
Thanks.
Yeah.
I always, sometimes I do this thing where I'll start explaining and I'll get into like talking about vapor pressure or something like that, and I'll think, oh my God, there's so much I can say about
Always.
this.
I mean, but that's the nature of science. It's all connected
Yeah.
in some way, right? But
Definitely. And maybe I'll just also throw in there that understanding little things like this can allow us to understand other bigger things, right? So actually the very concepts that I talked about here are really, really directly related to some of the concepts we're going to see in the science experiment later. Even though the science experiment has nothing to do with boiling water or even air. But the concepts are still relevant. So, you know, understanding core concepts like how molecules function and how temperature is really just molecule energy, those kinds of things can be really helpful in lots of different arenas.
Yeah.
gotcha.